This seems quiet. Can you hear me at the back? Yes, thank you. All right, everyone. Week 8. Here's Jay. Okay, what to talk about? Assignment 2 has been released. So here's your official notice. We got a few emails at the 11th hour before assignment 1 was due saying, oh my God, I didn't know assignment 1 was released. So assignment 2 is released. So if that's news to you, please be aware of that. Assignment live stream this week. I can't remember which day, but you'll get all the notices of that. Make sure you're keeping an eye on your emails and the forum. And the good thing about it now is you know the drill, right? You've done assignment 1. It's the exact same process. I will just remind for the 1911 students here, who's that? Who's a 1911 student? If you didn't opt into the 1511 assessments, technically to get full marks, you don't need to do the final 2 stages, right? So you only need to do stage 1 and stage 2. If you are a 1511 student or you opted into the 1511 assessments by completing that form, right, that we sent out, then you have to complete all 4 stages to get full marks. Is that clear? We tried to keep it as simple as possible. The live stream is tomorrow at 2 p.m. Awesome, thank you. And remember, it's recorded, so if you can't make it because it's not a scheduled event, that's fine. It'll be up on the YouTube channel. Alrighty, any questions on assignment 2's release and the process and all of that? Otherwise, it's exactly the same thing, except it's all about linked lists, which we're talking more about today. And you can still hear me at the back? Sort of? Yeah, it feels quieter. Give me a second here. How's that? Does that do anything? Hello? Hello? Yes? Okay. No one's giving me. Can you hear me at the back? Yeah. So they're saying sorta, but it's on full volume, so I don't know what to do. Hello, hello. Okay, that's the best I can do. I'll speak up. Hello. All right. Oh, when will assignment 1 marks be released? The answer is as soon as possible. Obviously, we need to mark them all. We're usually pretty quick, about 2 weeks. Sorry? Wednesday. Yeah, before assignment 2 is due is the best we can do. Yeah, roughly about Wednesday next week. All right, let's keep the noise down, please, a little bit, and then we'll get into this. So let's have a quick look at last week's topic, linked lists. So we introduced the concept of linked lists. Does someone want to yell out what a linked list is? What's the idea behind a linked list? An infinite list. What's it good at? Good. That's a reasonable answer. What are linked lists good at that maybe arrays aren't so good at? Having an undefined number of elements, we can say. Yeah, I mean, arrays can do that too because we can grow them. The thing about linked lists is that they're cheap. And remember, I'll just remind you, when we say cheap or expensive in this context, we're talking about computationally cheap. So it doesn't take a lot of process time or memory acquisition to add a new element to a linked list. Whereas with dynamic arrays, it can be quite expensive to expand them even a little bit because the entire block of the array, the entire block of memory may need to be reallocated. That's the problem we're solving with linked lists. They're a useful data structure. They're used in lots of applications. And also, the other thing we didn't really talk about last week with linked lists, that we're not really talking about in this course at all, but it's just useful to know that linked lists are a base data structure for many other data structures. Have you heard of a tree data structure? You might have heard of it. It's basically a linked list that can store multiple nodes at each node, rather than just a single node, if that makes sense. So this data structure is really useful. You'll learn more about them and its family of data structures in 1521. We looked at constructing a linked list specifically by learning how to insert a node at the end of a linked list, or the head, the beginning of a linked list. That's why we sort of constructed our linked lists backwards. And we made the head node point to null, then we made a new node point to that head, and so on and so forth. We learned how to traverse a linked list, which is essentially printing them. Now, here it says we did insert a tail, but we didn't do it, so we'll do it today. Then, depending on time and scope and all of that stuff, we'll look at inserting anywhere within a linked list, so inserting at a position. And this will also motivate why linked lists are fantastic, because with arrays, this can be quite difficult. So I'll explain all of that. Yeah, inserting in the middle and handling edge cases, like if there's only one item in a list, and deleting from a linked list. Yeah. All right. But let's do a recap, because linked lists are, I think, the final pivotal concept of this course. So let's spend some time on them. A linked list is a chain of nodes. And when we say node, we are talking about a struct. I said it says usually allocated on the heap. I would say always allocated on the heap. I can't imagine an in-stack linked list, but I may be wrong. I've never seen one, at least. It contains a payload, so some data. And the reason I'm saying payload here is that the linked lists we did last week were integers, but don't get confused, right? That can be anything. Could be another atomic data type, like a double or a float, or it could be a struct, or it could be an array. We don't know, it could be anything. So it contains something. And always, for a linked list, it contains a pointer to another node. And that's how I construct the chain of linked lists. So again, with an integer as the payload, this is something like a linked list struct declaration, a node declaration. I saw when I was looking at the YouTube chat from last week's video, someone asked, is next a keyword? And Brianna answered, but I thought it was a reasonable question. So we're choosing the name next here, right? Just like we chose the name data. Or just like any struct, we choose the name of the struct, the name of the properties of the struct. So we're choosing the name next because it's a really logical name. It's the pointer that stores the next node in the linked list. But this is a term that we're just coming up with, right? This is more defined for us. We need to point to another struct node so that I can chain my linked list. So I create some struct definition, and then I chain up a bunch of linked lists, a bunch of nodes. So the next pointer stores the address of another struct in memory. Right, we saw all of this last week. All of this lives on the heap. The heap is sort of unmanaged data, unmanaged memory. And so we need a way to refer to where that linked list starts in the heap. Right, so we typically always have a variable down in the stack somewhere, maybe main, maybe some other function, that stores the address of where that linked list starts. So what would happen if we lost this variable here, if we lost that address? Yeah, the linked list, exactly right. So the answer, so Jay just said the linked list would still exist in the heap, which is true, but it would be inaccessible. And actually this would be a kind of big problem because we would have no way to find it and free the memory. So not only would that be a memory leak, it would be a memory leak we can't recover from. More sophisticated languages would later come up and say, hey, well, if I ever have memory in the heap that is not referred to in the stack, free it, because it knows that you could never recover. And that's a memory managed language, but none of that exists in C. Okay, how do we know if we're at the end of the linked list? I should say linked list. Let me fix it now, actually. So an answer while I'm fixing this? How do we know? We store the final node's next address, we store the null pointer or the null memory address. We spoke a bit about null last week. Someone else want to yell out what null is? Anyone online, Brianna, saying what null is? What is null? No hand there. Pointed to nowhere. It's pointing somewhere, but you're sort of right. Pointing to an address whose sole purpose is to point back to main. I don't think it does anything like that. It doesn't point back to main. Nowhere was probably closer. So the null memory, oh yeah? Points to zero. It points to a piece of memory that is marked to be null on the operating system. And it represents sort of null. So it's an equivalent of the null terminator in terms of pointers and memory addresses. And we know if we're pointing to null, it represents sort of the end or nothing. And so that's a fully constructed linked list. So we defined the struct for the node. We have a pointer to keep track of where that linked list starts, right? Because we usually malloc the node and we get the memory address from malloc. And then we can connect it up. All right. So this is asking you guys if you want a demo of only the linked list concepts from last week. So I know a lot of people were still focused on the assignment one. Do we want to spend more time looking at last week's lecture code? Yes? Yes? All right. So here is last week's lecture code, and I've copied it, I've duplicated it into the week 8 code directory. That should all be synced up for on the course homepage. Let me know if there's any issues. Do we just want to run through the code and just get an understanding of what's going on before we expand upon it? All right. So up here, is that a hand or no? Up here, we have that struct declaration. And once again, we're storing an integer and the next pointer every time we have a node. It's pretty straightforward. Let's look at the create node function first. So we create functions that do the common actions that we need to undertake on our linked list. One of the core things we need to be able to do is create a node. So when we say create a node, we mean instantiate one of these node structs on the heap. So we pass in as parameters the data that we're going to store in the new node and the next pointer, if we have one. This is sort of the key line of this function, right? This is what you want to get an understanding of. So we're mallocing enough memory to store a node on the heap, right? Because malloced memory is stored on the heap. And we take that memory address back and we store it in a pointer to a node called new node. Yep. Then all we're doing is placing this data that was passed in the parameters into that node on the heap.
Usually that syntax requires thing on the left. Why isn't it malloc side struct node equals struct node new node? Why isn't that way around? You're redefining the malloc equals struct.
Say that again, sorry?
Are you not redefining the malloc or defining the malloc on the struct, not the struct?
So I'll try and answer the question in the way that conveys what was asked. When I say that we do the right side first, I'm always talking about the assignment statement only. So this happens first. This side of the assignment statement. Then I would say this happens first. We calculate the size of a struct node. That gets passed into malloc. What does malloc do? And what does it return? So he said creates memory, which is correct. And returns the address and assigns it to this new node pointer variable. Yeah. That's the order of operations there for that line. I don't know if that answered your question exactly, but I didn't quite catch it. Okay, then we take that new struct that's been initialized on the heap and we put the data into it. And then we return new node. So we return the memory address that was ultimately returned back from malloc, right? Because like we said in the slides, we need to know where that node is on the heap. Does that make sense? Whoops. Let's actually go to main next. So main is using these functions to do stuff now, to construct a linked list. So we call create node, we're giving it the element 4, and we're pointing to null. So we're saying, right, because we have nothing else to point to, this new node needs to point to null, aka it's the only element in a linked list, and it has no next. We store that memory address, because remember, create node returns the memory address, into a pointer variable called head, which is a pointer to a node on the heap. By doing that a few more times with different data and chaining the next node, right? So this node will point to head, which at this point was this node. This node will point to head, which at this point was this node. We are constructing a chain of linked list nodes. Then we print the linked list passing in the head pointer. And if we look at print linked list, it's kind of simple. We pass in the pointer to a node. We create a new pointer called current and make it also point to where head points to. Now, if you've got a keen eye, you might be asking here, why did we bother with current? Because you could just iterate through head, right? And the reason is if you do that, if you reassign head, you lose track of where the linked list starts. Now, in this case, it's not a problem, but it could be a problem in the case that you want to return back the head of the linked list. So some of the functions we do today, you'll see that pop up and it'll make more sense. And so just to be consistent, we can create this current pointer here. Then we have the precondition check. While current is not equal to null. Now the reason this is important is for two reasons. What's number one? Well, what's a reason we need to check this? Someone else, maybe? And then I will answer your question. So you said when it's null, it means we're finished. But there's just a really simple answer first. It's that the linked list could be empty. We could have passed in null, actually. Take another step back. The problem is if I tried to read if I tried to dereference current.data while current was pointing to null, that would be a seg fault. The program would crash. We can never read or dereference a pointer if it's null. So we always, pretty much, anytime we're dealing with this, we have to check that it's not null. Now, it could be null, like I said, for two reasons. One, we passed in an empty linked list. Two, which is what you're saying over here, we iterated through the linked list and we got to the null at the end. And if we didn't have that safety check there, we would dereference null and we would crash. But while we're not at null, we can read the data and print it, and we can iterate. So I want to say my current pointer, which was pointing to head, now points to wherever head was pointing to in the next pointer block. And that's traversal. We don't need to return anything back. Why? Because it's just printing. It's not doing anything. All right, and that's it. That's the code. Any questions? Any questions online? Guessing not. All right. Then shall we do, what did I say? Insert at tail. So in this program, we only had one way to insert, which was essentially by using create node and this next pointer. So what we want is to create a function which accepts a linked list and adds a new, not a new linked list, I keep saying that today, a new node at the end rather than the start. If we look at create node, it's putting it at the start because it takes the node that was passed in, or sorry, it takes the node that was created and it sets its next to be the node that was passed in, which means it has to be before it, right? Sorry? Rename this, you're saying, or just talk about it? Sure. Okay. Yeah. I'll do that here in a second. So create node was adding, prepending is a nice term. Prepending to the new node. What we want to do here is append a node, at the end of the links list. So simple idea, but what we'll see quite quickly is that doing it is a little different. The other thing we'll need to pass in here is the data. So that can be the same. We can just say that the caller passes it in. Now, to be consistent, I guess I actually think that I prefer it like this. Does anyone else agree or disagree? Yes? Tim? You disagree? I'm going to listen to Tim. But we should just keep it consistent regardless. So data will be the new data in the new node that goes to the end. We'll let main pass that in because we don't know how they want to gather it. Maybe they want to scan it in, maybe they already know what it is. All right. So if we think about it, let's go to Figma. That's not Figma. I mean, hopefully this is not too messy for you guys to get your head around. If we think about this diagram here, and we think about our function that we're writing, insert at end or insert at tail or append or whatever, we pass in the head of the node, right? So we're passing in this is all we have at the moment. Do I know how long the linked list is? Right. Also, I never answered your question. Did you have a question before? Okay, sorry. I forgot. So you said we don't know how long it is, which I agree with. Let's just stop there for now. We have a reference to this node here, this linked list. We don't know how many come after it. We don't know. So how do we insert at the end of the linked list? What would we have to do? Yeah, you have to traverse through the linked list. And this, I guess, if you think about it, it's pretty cheap to do, but it's not as cheap as an array that already has enough memory where you can just insert at the end. But basically what we have to do is follow the pointer, dereference next, follow that pointer, dereference next, follow that pointer, dereference next, find the word null, and now we know this is where we can insert, right, a new node. We no longer point to null and we should point to there. Does that make sense? I didn't get any response. It makes sense.
When we normally declare a new struct on the stack, it has a name, but do these like nodes not really have a name? Like they're just chained up.
So the question was, when we create like a struct, for example, on the stack, it has a name. And the reason you say that is because the only way we can allocate memory on the stack is if we create a what? Variable, which has a name, right? You're right. That's the mechanism for allocating memory. On the heap, it doesn't work that way. We don't create variables. That's not the mechanism in which we allocate memory. We allocate memory by calling malloc, which just returns back where it was created. It's up to us to decide if we want to associate that with a variable which is named. We sometimes do that. If I say int pointer to data equals malloc size of int, I've created a variable which points to the heap. But I don't need to store it in a variable. There's no names in memory, right? Variable names aren't stored anywhere in memory. They're in the code. All right. What was I saying? So we've got to traverse through, basically, is the first thing. We've got to get to the end of the linked list because we're inserting at the end. If only we had a way to traverse through a linked list, and in fact we do. We traverse through when we print. So I'm going to copy it. Now, obviously, we're not printing anything, so I'm going to delete those two lines. So I'm going to copy the logic for traversing through a linked list. Let me get rid of that so you can see it. Now, let's think about this code in a slightly different way to the way we thought about it in print linked list. When we were printing a linked list, all we cared about is finding the next node and printing it. But in doing that, when the loop ends, when current is equal to null, it also means we assigned current to be the final node in the linked list. In fact, we go beyond the final node and we go to the point in which current is null. We actually follow it too far. Is that making sense? Because we say current is equal to current.next. In the final loop, current.next is null, which means current is assigned to null. Then we fail the check and then we end. So we've got a bit of a problem here. We've looped one too many times. At the moment, as that is how the loop condition fails. What we want to do is, if we go back to our diagram, is loop until, let me undo this, loop until current is here, right? We want to get to this point because here we can hook it up to a new node. But if we do what we're doing at the moment, we go one too far. Does anyone have a solution to this problem? Not Jay, maybe you.
So it should be like while current next is not equal to.
Very good, very good. So what we just said here is, instead of looping while current is null, or why don't we just loop until current.next is null? If you look back at the diagram, if this is current, what is current.next? What's current pointing to? I'm not getting much from the audience. What's going on? Everyone's tired. Where's current? Current is here. Follow the arrow. What's the data at current? 4. What's the next? Yeah, that means we're at the end. Do you see that? reassign current to current.next until is null. All right. Now, this brilliant solution actually introduces another problem that we should fix before we proceed. Does anyone spot it? Surely someone online. What's going on? Everyone's pretty tired? What was it, assignment 1 or just life? Okay, good to know. Can't help you with that. And yeah, anyway. No, that's fine. It's all right. We'll take today a bit slower. Ooh, so what's your name? Max yelled out, when the linked list is really short, you have problems. You're on the right track, but we can be a bit more precise. Let me give you guys a hint. This function didn't have the problem. The change we just made introduced the problem. If you think about here, this function, print, what happens if I passed in null as the head pointer? Oh, hold on, you first.
You're trying to access next, but the head is null.
Well, sorry, you're right, but answer my question first. In print linked list, what happens if I pass in null to head?
Oh, it just doesn't run the while.
It doesn't run the while loop because we checked that it's not null. We have the safety check. Before we do anything to current, we check that it's not null. You're right. The problem we introduced by doing this is that now do you want to answer it again?
Oh, if the head is null.
If the head is null, so if current is null,
you can't get next from null.
We can't get next from null, exactly. Because to get next, we have to dereference current. Remember the arrow operator dereferences. But if head is null, we are trying to dereference it to check next. So you're absolutely spot on. All right. So what we need to do is say something like if current is equal to null, you got two options here. You can create a new linked list node and return it because you had an empty linked list. But you can also just return null, I suppose. What do we usually do? Now I need a reminder. Tim, Angela? We return the new node. A new one. Yeah. Right, okay, yeah. So we can say return. We don't even need to do that. The size of no, I don't do that. Oh yeah. Thank you. Yep, thank you. So if we passed in an empty linked list because there was no data, we can just create one and return it. So this is a boundary case handled. This is really important, this idea of checking and thinking about boundaries. It would be very, very easy. Let's think about it, right? This is now like a bit about software engineering rather than computer science. It would be, well, sort of. It would be very easy to think about this function and forget about this boundary case, right? Can you see that? And it would be even easier to write all of your tests, write your code, and never pass in an empty linked list, because you just don't think about the fact that you could pass in an empty linked list. And then someone will use your program, and what would happen? Like potentially in some case, if the empty, or if you write this code and you're providing the code to someone, they could pass in a null pointer and your program would crash. So this is where we got to think about the extremes or the boundaries. Empty linked list, you could say very large linked list, but that would be fine probably. Things like that. All right, so this is a boundary case handled for empty case. All right. This traversal will end when current points to the final node. In fact, let me put this here. So at this point now, then we iterate through, we know we don't have an empty list. We could iterate 0 to many times. Okay, here's another boundary case. What if you've got a single node in your linked list? If you have a single node in your linked list, this won't return true because current is not pointing to null, it's pointing to a node. Next points to null, which means this will fail. This will fail immediately because next is pointing to null, and then we're in the same position, so we're fine. By default, we handle the case of 1. So now current points to the last node. We need to create a new node. Now, what's next going to point to? If we're adding at the end, what is next going to point to? Null. It's the end, yeah. But what do we have to do to current? We don't want to reassign current. Remember, this is current. Oh, someone said it. Who said that? Who just yelled that? Where are you? There. Change the next. Exactly. At the moment, the next is pointing to null. But we've just created a new node. We want the next to now point to that new node. Yeah? So we could do two things. We could create a variable which points to that address. Or we can just say current next is equal to the memory address returned by create node. And that's it. I know you guys are discussing how beautiful this solution was, aren't you? One more thing. This is also the situation in which we've changed, well, not really, but we can return head here. The reason we might need to, well, yeah, now we make sure that whoever called it, whether it was the empty case or the new case, gets back the pointer to the start of the linked list, be it the same linked list that was passed in or a new linked list. Have I missed anything with this, guys? This looks good. Do we want to test it out? So now we don't even need to call create node here. We can call add, no, what was it called? Insert a tail. Whoop. Whoops. Thank you. Line 18. Oh, I see. So I can use my function prototypes here to make sure that the order of my functions don't impact the program. We should get something like 4, 6, 8, 10 null. 4, 6, 8, 10 null. And this is a little bit nicer to think about because previously, if we think back to the week 7 one, the only way we could construct our linked list was by constructing it backwards because we could only insert at the start of a linked list. Now we can insert at the end. Although, which is more efficient? The start, because now we have to loop through the end every time. But this is more useful. Or it's a trade-off at least. All right, that's insert at tail. Yeah, insert at end. Any questions? No?
Are there certain scenarios where it's better to insert at tail or insert at head? How do you really decide what?
So the question was, are there certain scenarios where it's better to insert at tail and insert at end? You're thinking about this in terms of constructing the linked list from scratch. You need to think about it in terms of, what if I've already got a linked list? Then the answer is, well, it depends what you want to do. Do you want the new node at the start, or do you want it at the end? If you're thinking about constructing from scratch, I just said inserting at the beginning is more efficient because you don't have to traverse. Traversal still takes it's very cheap because there's no memory allocation, but you still got to dereference the pointers and move along. We're doing middle today. Insert at middle we'll do today. Here and then here. Oh, yep.
We can optimize our create node function because you don't need to pass to the next point. Because every time we're calling it now, it's always going to be null.
But someone could still need to create it manually. No?
Yeah, I think it's just that all of our sample solutions will have it not with the second.
What? I'm gonna leave it, but it's fair. Yep. Yeah, that's right. True. That's also true. If we want create node in the middle, create node needs next. Anyway, yeah, that's right. Okay, it doesn't matter. Forget about it. Any other questions? All right. Should we do our lecture break now? I think you all need a coffee. If I had the budget, I'd shout you all, but I don't. 5 minutes. Have some water, have some coffee, come back with renewed energy, and we'll keep going. Hmm? Oh. Alrighty, shall we start? All right, let's go. Ignore the title, I guess. Very good. I mean, memory is not incorrect, but if you can, we should be more specific. But too easy. I'm hoping this is not a duplicated Kahoot. Oh no, this is different. Never mind. Why? What did you do? But that would be, how do you determine, I don't know, what's the function of the size thing? It says if you've got a struct node, how do you determine the size of it? You've got to pass in struct node. Who got it? Well done, well done, well done. What else did you guys do? Oh, that's right idea, right idea. You got screwed a little bit more. Yeah, similar. Yeah, okay. Can I give you the point? Oh, I'm not giving you the point. That's not right either. This would be the size of the pointer. So that wouldn't work. No, I'm not giving it. No, this would only work if node was type deft, which we haven't done. No. No. Who was this? Lucky. You owe me one. Wow, that was a lot of points. What is a condition to stop on the last node of the linked list? We just did this. So I hope you're paying attention. Yeah. Oh, you poor blue people. All right. If the current next is not null, then we keep looping. That's the condition. Such that we end up where the current points to the final node. If this was equal to null, it would never loop unless you passed in a single element linked list. Does that make sense? Oops, sorry, I just double clicked there. What is printed out on line 28? Oh yeah, awesome. Really readable. I don't know, look at your phone. No, zooming in makes it worse. I can't read it. Well, we haven't done deleting yet, but you should be able to get the idea, I think. Well done. So we delete the nth node and we're deleting node 1. So that will delete 0, 1, which is the element 2. So it'll be 1, 3, 4, 5. And then x meaning null. Any questions on that? We'll look at the deleting in more detail in a second. All right, final question. Hopefully you can read this too. That's better. Oh, well done. Who put that? You did very well. Very good. Second most popular answer was the number 1, which that just, you would assume that it added it. So why is this an error? We're dereferencing null. Let's think about it, right? We create head to point to null. That's what that line does here. So on line 18, we're calling insert tail. Remember, this goes back to what we were talking about with J. The right-hand side of the assignment statement always happens first. So what's happening? We're calling insert tail, passing the data 1, and passing head. At that point, what is the value of head? Null. So we're passing null here and 1 here. So current node points to head, which is null. And we're saying null.next. Do you see that? That's the problem. You can't get .next of null. There's nothing there. This is why we need to also test that current node is not null, or have an edge case that accounts for it. There's nothing to .next on. All right, very well done. All right, are you in the room? Where's the third person online? Well, come down. Come get your card. Is it you? No. Oh, do I? Debt collectors knocking on the door. So hold on. Who was Daring Koala? You? Congrats. Captain?
No, red dog.
Red Dog. So who was Captain Gator? Was it Brianna? Is it someone online? Oh, you get your first pick. There we go. Congratulations. Oh, I think that's a... Oh, whatever. What were you last week?
I was first on Monday.
Okay, then you can have first pick here. Awesome. And Captain Gator, if you show me a screenshot, I'll give you a card next time. Don't ask for coffee. All right. All right, let's keep going. So we spent a little bit of time on insert at tail. The good news is a lot of that detail is going to fast track us through inserted index. So let's do inserted index next. First of all, let's figure out what the hell we mean by insert at index. So all we mean here is insert at the position passed in. So if I have 1, 2 to 3 and index 1, we would have 1 to 1 to 2 to 3. Do you see that? So it's just showing us where in the linked list we want to insert. We pass in the position, the index. If you think about, I want you to think about something. If you think about having a dynamic array and you want to insert in the middle of it and it's full, what would you have to do? Create a new array that's bigger, and then you would have to move every single element over. Like, it's a fair bit of work. Well, the cool thing is with a linked list, it's not too much work. All right, so inserted index. What do we have to do here? If we go back to our trusty whiteboard, maybe I'll just delete that because it's getting a bit complicated here. Maybe I'll put this here. Just to streamline this a bit. Is that a bit clearer? If I want to insert a new node, like after 11 and before 4, so that would be the index 2, what would we need to do? Similar to inserting at the tail, we would need to traverse through until we get to index, right? Until the number of times we traversed is the same as index. So we are going to need to introduce a counting variable here. Head is not part of the linked list. It just points to where the linked list starts. So you could say it's 0.
So index 0 in this case would be the one holding data.
Correct. Absolutely. Yeah. Head is not counted as part of that linked list chain because it's not a node, right? It's just a pointer. Yeah. So essentially, we do the exact same thing as insert at tail, except we have to count how many times we traversed. So I can create an integer called counter, for example, which counts how many times we assign current to current.next. So the first thing we want to do is just iterate through to the right point. Now, what happens if it's an empty case? Do we create a new node? That's a question that's sort of up to the implementation, up for us to decide. Because if you're saying, hey, insert an index 3, but I have an empty node, should you add it or not? It probably, to me, makes more sense to return null and just error out and say, oh, it doesn't really make sense. Does that sound right? So because we're not just saying insert at the end and insert at the beginning, we're saying insert us at a particular position. If there's no linked list, it doesn't really make sense. So we can just handle it this way. But you might decide in your, in your library for linked lists, for example, to do something a little different. Exactly right. That's right. We'll deal with that in a second. But the question was, what happens if we're dealing with a linked list shorter than the index passed in? So we'll have to come up with a case for that too. All right. Let me delete these comments. So the condition for loop, that was just for demonstration purposes. So the condition for looping is if we're not at the end of the linked list, which is the same here, and counter is not equal to index. Because if we're not at the end of the linked list and the counter is the same, we're ready to insert. And of course, every time we traverse, we add 1 to counter. Does that make sense? If that's confusing to you, the best thing to do later on is to whiteboard this out on Figma or pen and paper and add 1 to counter every time and see when it all matches up and see when it aligns. So at this point now, counter is the same as index. Let me just shut this door. Now, just thinking this through, the other time that this can fail is if we get to the end and index is not matching, right? Because we're saying both of these need to be true. So I suppose I can say if counter is not equal to index, do I just return it unchanged? Is that what we usually do? Yeah? It is a question for us to decide. We can decide it now. So the question is, if the index is greater than the length, should we put it at the end, or do we just not do anything to it and return it? You're saying add it to the end. No, Brianna's saying it. You're saying no. Yeah, I think so too. Yeah. They're both valid options. This is the thing, right? It's up to you to decide what should happen. For now, I'm just going to return head. I'm not going to change it. This isn't great because we're not really communicating back to the caller that it wasn't appended. But for our case, it's fine. So I guess it's this point now that counter must be equal to index. So we have enough space for it. And we're not at the end of the linked list. We want to add a new node after current. So this will do that. But there's a problem-ish, is that there could be data after current.next, right? So if we go back to Figma, we're here. If we create a new node, put it here, this points to this now. The problem is this needs to point to the old current.next, which was this is next, so that we maintain the linked list. So I think what we can do instead is say create node. Is that right? Yeah. Cool. So we created a new pointer. So we create a new node. It points to the current.next, right? The old current's next. Then the old current's next now points to that new node, which then pointed onto the new next, and we return head. All right, we'll have to test that I've handled everything okay here. So this is inserted index. You can see it's a step up from inserting at the end or inserting at the beginning because we need to rearrange the existing links. All right, so we have 4, 6, 8, 10. Then we print it. Then let's say I insert 7. At head. And at position, let's see. So let's go 2, I think. And then print it again. All right, let's see how this goes. There could be an issue. Line 63, I have an error. Oh, I thought I deleted that. That was just from when I was explaining something before. All right, so I'm off by 1 a little bit. So I suppose 1 would be here. I'm off by 1. Okay, yeah. So 1 would be here, 2 would be here, 3 would be here, which is sort of what I intended. No, I'm off by 1 in the other direction. 4, 6, 7, 8, 10. That is what I wanted. I suppose you could tweak. If you wanted it to be that, position 1 would be after the 4, you could just add 1 to the index, for example. Now, a function like this, you can see there's more edge cases than insert at tail and insert at head. You've got the same edge cases as before, empty linked list, 1 item in the linked list. Now you have, what if there's no existing elements after the linked list you're inserting at? What if there are elements after? What if there's no elements before? What if there are elements before? So you can see you've really got to think about all the boundary cases, test them through. There might be a few cases we've missed here, and that's fine. We can find them later and deal with them. But the core idea of inserting at a position is this idea. And you can see every one of these boundary cases, we typically have some sort of test to check for it. Cool? All right, that's inserted index. Why don't we do remove tail or delete tail first, because that should be simpler than deleting at an index. Or we can do size. What do we want to do first, size or remove tail? Size is pretty easy. You just want to escape this lecture. What do you want to do? Size? I'm going to base it off print. Size of linked list, we pass in the head. What would the return type of this function be? Int, exactly right. If you think about it, what do? We have to traverse each node, and we just have to keep count of every time we traverse. So it's really simple. We can do this. We can say int counter equals 0. We don't print anything, but every time we traverse, we can, I can't spell. We count, and then we just return counter. It's that simple. It's useful. This is useful. You can use this, for example, when you're boundary checking inserted index. If you want to check that the index is smaller than the size of the linked list, now you can just add a simple if statement to check that. However, be aware that you've got to traverse to count, so it can be slower. So that's size. Just check that compiles. Very good. That's side. You're not pulling up my typos either. Question?
Like store a variable on the stack that the running second counter of how long the LL is. So if you have the size of the linked list.
Could you keep track of a variable on the stack that keeps track of how long the linked list is so you don't have to compute it? The answer is that's a nice idea. In fact, an even better idea would to be put that as part of a struct which represents the linked list, so that it's sort of packaged together. You could do it. It's a trade-off. If you're referring to that size frequently, right? It's a memory versus computation trade-off.
Is the difference like
Insignificant? Yeah. Insignificant in modern day. Yeah. You would not notice it. All right. Let's do remove at tail. We haven't done removing yet. Let me also, to be consistent, forward declare these. All right. Remove at tail. Obviously, for removing, we're not passing in any data because we're not creating a new node, right? We're deleting a node. Let me just, whoops. Let me delete that. Let me keep that. Let me delete that. All right. Remove at tail. We know that we're going to need to traverse through the linked list again, right? To get to the final element. Let's actually go to the whiteboard and undo this. If this is our linked list, I want to remove at tail, which node, or what's the value of data for the node that I want to delete? Say it louder. 4, exactly. We want to delete this one. If I delete this node, what am I going to have to do here to complete this linked list? Point the second last element's next pointer to point to null. Exactly right. Exactly right. So there's two major solutions. Two approaches. I can have a second variable which refers to the previous to current, right? So if this is current, this would be previous, so that I can set previous.next to point to null. Or I can loop while current's next is not null. So in fact, what I can do is just loop until I'm at the second last node. Both are valid options. Do we have a preference? Do we care? I can show both actually, because they're both valid. So the first is that we can do this. I create a new pointer. Remember, pointers are very small, so we don't really care about creating the memory to do them. Although I think it would be, this is, less efficient. Let me do the efficient method. All right. We always got to think about the empty case. What happens if null is if current is empty? Sorry, if head is empty, we would just return null. We can't delete something that doesn't exist. What if we have one element in the linked list? We would want to delete it, right? This would be well. Let me not do that. So this loops second last node. Although this could cause a problem, right? If the first next is null, I'm just thinking. So I might actually do it what I was going to do. So now every time I loop, I update my current to move to the next node. But before I do that, I assign previous to point to the one before, to current as the value of what it was. So previous is always going to point to what current was, and then current will go forward one element. So here, what I need to do is I need to say previous dot next is equal to current. Sorry, is equal to null. Free current, return head. So let me go to the whiteboard and whiteboard this. All right, let's whiteboard this. So we start off, current is pointing to the head node, which is here. Previous points to null. If current is equal to null, which it's not, so we don't worry about it. While current's next, which is here, is not null, which is true, previous is equal to current, which is here, and current is equal to current.next, which is here. We do that until current.next is null, which would be here, and previous would point to here. Right? Because current next is null, previous is the one before it. Then we say previous.next is equal to null. So instead of pointing here, it now points here. And we free current. And if you look, head points to 8, 8 points to 11, 11 points to null. We obviously would eventually delete previous and current, and we've removed from the tail. Now, I think there is an edge case that hasn't been accounted for here, which is if there's only one element in the linked list. So let's think about that. If there's only one element in the linked list, it would look like this, right? Current would point to head. Previous would point to null. Now, current is not null, so that's fine, but here we would fail immediately. Current.next is null, so this would not run, this would not run, and we would try and dereference previous, which is null, so that's a problem. Do we see that? So we do need to check here if previous is equal to null. If that's the case, all we want to do is free current and return null. And we don't need to hook it up.
Can you please explain why did we do these 3 lines again?
Why do we do these 3 lines? This is for the case that previous was null. The problem is this dereferences previous. So if there's only one element in the linked list, so current points to that element, what does previous point to? Nothing. And then we would try and dereference nothing to get next, and it would crash. So on the case that previous couldn't point to anything because it didn't even have one chance to iterate, we have to handle that edge case. Again, it's another one of these edge case states. If there was something in null, in previous, then hook it all back up. Make sense? Someone said no, fair enough. It'll take some time, I think, to process these functions. Time, practice, whiteboarding, pencil and paper, things like that. All right. So we've done remove tail, we've done size, done insert. We've got delete node at index, which is probably the trickiest. What are the slides that I have? Okay, this was inserting and deleting. We've done that. All right, yeah. Let's look at delete node at index. We're all up to the challenge? I don't know if I am. Let's see. We're dealing with an index, so it's going to be similar to inserting it in index. So we can base our solution off this. Did I also do remove it tail? Oh, also, I should probably test that compiles. Very good. All right. Actually, I should test that it actually works as well. Insert at index, we print it. Then we have, was it delete? Remove it tail. And then we print it. Four, 6, 7, 8, 10 null, 4, 6, 7, 8 null. So that worked quite well. Good. Always, yeah, test frequently. That wasn't very good of me. All right, so now we're adding delete at index. So we need to pass in index, the head node. We obviously don't have data to pass in, right? We're deleting here. Also, I've got delete and removed used interchangeably. I don't like that. So let's just make that consistent. All right. What else are we going to need to do here? Will we need a counter? We need a counter because we need to count that we're at the right position. But if we're deleting, and especially if we're deleting in the middle of a linked list, what else are we going to need to do? We just did it. We're going to need previous. Is that what you meant? Yeah, I guess so. Just take ownership of it. We're going to need a temporary variable or the previous pointer because once we iterate up and we need to hook previous to point to the one that current was pointing to, right? So we need previous. Okay, good. Empty case. If the linked list is null, we can't do anything, so we leave that case the way it is. That makes sense. Let's think about the traversal. We want to traverse until the end of the linked list, and also until current is the same as index. So if current is not, a counter is not the same as index, we keep looping. At some point, counter will match index, and now we're at the position where we want to take the previous and hook it up to the currents next, and delete current. And we also need, every time we traverse, we need to assign previous to be the same as what the current is. Then current will go to current.next, and we add one to the counter. So there's a lot going on here. This is the case where we are at end of list, but counter is less than index. Right? Because for this to be true, we had to stop looping, which meant current.next is null, but the counter didn't match the index, because counter doesn't match index. At which point we're saying, well, we can't delete anything because the linked list is shorter than the index that was passed in. All right? So that makes sense to me. Here, we want to delete current and hook previous to point to current next. So this is what we're trying to do. To get to this point, to get here, we are not at end of list. We could be at the end of list. Counter is index, so we're at the right position. And we are not beyond end of linked list. And so it's at this point we want to delete current and hook previous to the point to the currents next, and then we free current. And we've already done that exact logic. Remove it tail. I'll think about that case later. So what we want to do is take previous, and its next should not point to null. What should it point to? Current.next. Who said that? Well done. Whatever current was pointing to, previous should point to it. That could be null, but that's fine if it is, because that just means we insert it at the end anyway. And then we free current. Now, did we handle the case where we only looped once? I think it's just a matter of this exact same logic. It's not working? Oh, unrelated. I think it's the same logic here. So if previous is null, so there was only one item in the list, we free current and return null. I think that's right. Is there any other boundary cases that I'm missing? Jay looks defeated. All right, let's test this. This is remove at index. I might just add a few more elements. I don't know why I'm going up by 2, but I'm doing that. I'm also going to say what I'm doing. So Right, so now we can sort of quickly check that it's doing what we think it should be doing. All right, what am I doing here? Line 180, remove it index. I've got that the wrong way round. So 4, 6, 8, 10, 12, 14 to null. We insert at index 7 value of 11. What? That's not right, is it? Value 1. And that should be at... All right. We insert at index 1 value 7. So that's the new value. I think you could argue here that we're off by 1, maybe. So we've got to minus 1 in the inserted index function. Is that right? That looks right to me. This looks better now. It's 0. We'll deal with that later. Yeah, exactly. Or we won't deal with it later, but yeah. So we inserted index 1 value 7. So that 7 got added. You can see that, everyone. Then we remove it tail, so the 14 gets removed. Then we remove an index 1, which would be the 7, and the 7 is gone. Right, so those are a lot of the building blocks for linked list functions. Now, all right, that's a good place to leave the lecture. Look at these notes I've got here. I noticed everyone was pretty wrecked today. Whoops, where's my pointer? Hello? I'll do the question in a second. There's a lot to get your head around, right? When you're thinking about navigating these structures. Take your time through it. Don't let it overwhelm you. No, whiteboard it. Discuss it with people. Go to help sessions. Go to revision classes. Question at the back. It's always published. Okay, where do you find the live code for the lectures, everyone? On the website, in the current term. Go to lecture code, week 8. There's linked lists, see? It's live. Yep. All right. There's the feedback. I know that was a lot of content and everyone seemed a bit wrecked, so try to get some good sleep. I'll see you on Wednesday. Hey.
I got a question. I looked through the code and I don't know where the program knows what valued index is.